And to kick off today's keynote lectures, we'll be hearing from the physicist Juan Ignacio Cirac, one of the pioneers of the quantum computer. Juan Ignacio Cirac is one of the directors of the Max Planck Institute for Quantum Optics and honorary lecturer at the Technical University of Munich. His work has earned him numerous awards and accolades, including the Príncipe de Asturias Award and the Wolf Award. The title of his lecture is Quantum Technologies, from Schrödinger's Cat to a New Era in Computing. Professor Cirac will be our first speaker this afternoon, so please welcome him with a warm round of applause.
Hola, muy buenas tardes.
Hello, good afternoon. Good afternoon, everyone. It's wonderful to be up here looking at all of you with your eager faces, hoping to learn something about science. As a scientist, this is a unique opportunity to be able to be here amongst all of you. So I'm very, very grateful to the DIPC, to the organizers of this event, for having invited me and giving me this privilege. I come from the Max Planck Institute for Quantum Optics. And this morning, there was a fantastic piece of news because one of our colleagues, one of our directors, was actually awarded the Nobel Award for Nobel Prize for Physics, Florence Klaus. He has been a collaborator of Pedro Miguel Echenique, and he actually asked me to say hello to Pedro and his whole team. So, I'm going to be talking about quantum physics today, and it's entitled From Schrödinger's Cat to Quantum Computing. Now, I don't know if some of you remember this, if you were here in 2019. I gave a talk about quantum computing. It was just the beginning of October of that year, and when I finished my talk, I said, we are just about to have a major breakthrough in quantum computing, because there were rumors around at the time that there was going to be an announcement of some results, and we were going to announce the fact that the first quantum computer had been able to carry out a calculation that, if we had done that calculation with normal non-quantum computers, it would have taken a very, very long time. And in fact, a couple of days later, we can see here in the headlines in the New York Times that Google claimed a quantum breakthrough that could change computing. They'd chosen an academic problem to try out the capacity and the power of these quantum computers. It was a major revolution. It came out in all the newspapers, hit the headlines all over the world, saying it was going to change our lives, how quantum computing was going to have a major impact on different areas of life, industry, etc. It also was going to change our politics as well, because politicians suddenly realized that quantum computing could be a key technology for the future, and they decided that it should be probably a good idea to invest in that before all your competitors invested in it. So it changed the political landscape as well. And many companies, private companies as well, were already building quantum computers, not just Google. This is a list of some of the companies that in 2019 were already working in that field. Today there's about 500, 600, 700 companies, startups, large companies, all sorts of different enterprises who are designing and building or prototypes of quantum computers. And they're studying their different applications. Particularly, here in the Basque Country, we're a center, we're a hub where quantum computing is going to have pride of place, because we have reached an agreement with IBM, and it's going to be one of the 6 or 7 quantum computers designed by IBM, which are the most powerful ones in the world at the moment. It's going to be here, and we're going to be using it to carry out research, and it's going to help industry, and we're going to be able to use it. But besides quantum computers and quantum technologies appears and is important in other areas as well. For example, communications. Over recent years, in newspapers, we've seen how quantum communications have been achieved between different cities or with satellites. Communications which are much safer and can't be decrypted. So it's a way, there's a way of encrypting messages based on quantum physics, and it cannot be decoded, it can't be decrypted. There are also applications in the field of sensors to process data more efficiently. Many companies are analyzing how this can be used in the medical field with medical devices which collect a lot of data, and how we can interpret that data in order to predict certain elements of the future. There are other applications as well. There's quantum money as well, and this is a fantastic moment because everything's really taking off. Quantum technologies are taking off. Now, my aim in today's lecture is to explain to you what quantum technologies actually are. And that's going to take up most of my lecture. I'm going to try to make sure that those of you who are not experts in quantum physics here will understand what quantum physics, quantum technology is, so that you'll be one step closer to understanding what quantum technology is, because it's going to change our lives over the coming 20, 30 years or so. Then I'll talk very briefly about what's the point of it, what can it be used for, when will these technologies be available, are they available now, and if not, when, and how we can get ready for them. There's going to be more lectures. There are going to be more lectures on quantum technologies in the Passion for Knowledge Festival. So some of these questions will be answered, especially the last three will be answered by other speakers. So I'm going to be focusing on the first one. I'm the first person to be talking about quantum technologies. So, trying to explain quantum physics to an audience that has no idea about quantum physics is not an easy task, but I will do my very, very best to explain it clearly for you. So, quantum technologies are the result of a combination of two different disciplines. Quantum physics, which describes the microscopic world, the world of the tiniest, smallest particles that make up all of us and everything that surrounds us. So it's a combination of quantum physics and information theory. These two things together give us quantum information. And it was Max Planck who first started to talk about quantum physics, and Shannon was the first person to realize that information is a physical quantity. It's like mass. It's something that can be measured in kilograms. It's like a distance. It can be measured. I could be given two books, and I can measure how much information is in one book and how much in the other to see which has more information. So information can't only be measured, it can also be compressed. So I have a book that repeats itself a lot. I can compress it to make it a thinner, lighter book. Information can also be corrected. If I have a book and someone crosses some things out, then I can reproduce what was there beforehand, so I can correct information. So this is information theory. Now, when we combine information theory with quantum physics, it gives us a different way of dealing with information. It's quantum information. It's a different way of processing information, firstly. And if we process information using the laws of quantum physics rather than the laws that govern normal computing, but with the laws that govern the microscopic world, that gives quantum computing. Now, if we transmit or convey that information to someone else using the laws of quantum physics, then we have quantum communication. And if we acquire that information, again, using the laws of quantum physics, then we can have metrology and quantum sensors and quantum metrology. So this is sort of everything that we're talking about. We're processing, transferring, and acquiring information using different laws of quantum physics. And every time we do that, every time we use new laws of physics for something, then a whole range of different possibilities open up in front of us, and we can really make the most of the advantages of the quantum world. Now, I'm going to be talking now about quantum physics, which is my area of expertise. So to start talking about quantum physics and to understand how quantum physics can help us with information to process, transmit and acquire information in a better, more efficient, safer way, first of all, we have to understand that quantum physics is around us all the time, but we can't see it. It's in the microscopic world. In order to get down and see what happens in the quantum world, we have to really, really get down to the microscopic level. We have to immerse ourselves in the microscopic world. We're talking about really small things. We can't see these things with a microscope. We need really special equipment in order to really see these tiny, tiny things. We're talking about the size of an atom, of an electron, of a photon. So we really need to get down to that level. And when we get down to that level, when we immerse ourselves in the microscopic world, it's like going through the mirror in Alice in the Looking Glass. because things just are really, really different from what they usually are in the normal world. There are different laws, the laws of quantum physics, and those laws are completely different from the laws to which we're accustomed to in the normal world. It's like going into a Lewis Carroll novel. So what is quantum physics? It's the theory that describes this microscopic world. It was first described by Max Planck in 1900, so it's quite an old theory. And it enables us to describe the very, very, very small things all the way up to our world. So we have atoms made out of elemental particles, and how atoms get together to form molecules, and the molecules go together to be solid, liquid, or gas, and how that all behaves. All of these elements comply with the laws of quantum physics, and they comply to the letter. Today, we can actually make a prediction about how one of these very small particles is going to behave. We can predict to 17 decimal places. So, according to the laws of physics, we can say it's going to behave exactly like that. And we can see this because we carry out some very complicated experiments, and we can see that this theory is always adhered to. It's very, very precise. So even though it might seem a very strange theory, it's a theory which we know very well, and we're able to use it to come up with some very, very precise and accurate predictions. But quantum physics, well, it was developed a long time ago, and it gave rise to many of the things that we have around us, transistors, lasers. All of these are based on quantum physics. But right from the very beginning, the pioneers of the field of quantum physics realized that if we believe in quantum physics, that actually has some repercussions that seem sort of closer to philosophy than to physics. And this is what gave rise to the debates and the arguments between Einstein and Borg, for example, in the early 1900s, because they simply couldn't believe that nature could be quite so extraordinary. Because according to the quantum theory, in the tiny, tiny world, the properties of different objects are completely different, and they all behave really strangely. The properties of certain objects aren't actually defined. So, for example, I'm in my macroscopic world now, and I can see that the podium's up there and there. The property that's position is defined. It's there. It's not going to move by itself. But if we go down into the microscopic world, this is no longer true. The properties of objects are no longer defined. An object might be in many different places at the same time. And this is quite an extraordinary and very, very strange property. We all find it strange. It's not just you, if that's what you're thinking, but that happens. That happens while the object is isolated and not observed, but as soon as we observe it, then that property becomes fixed. Now, there's a very, the explanation is very complicated, and physicists, we spend a lot of years studying this, but if I had to just sum it up, I would say the following. Quantum physics says that in the microscopic world, when we've isolated things, the life of these particles, if they are isolated, it can exist in various universes at the same time. In one universe, it's in this position, in another universe, it's in another position, etc. And these combinations of universes which exist at the same time are what we call superposition. So in this microscopic world, we have these superpositions of different universes. The properties of particles are not defined because in each universe, the properties are different. Which is why we say that properties are not defined. And what quantum physics tells us is that when we look at it, so when that particle is no longer isolated, when we look at it, that's when the properties are fixed. So all the other universes disappear and only one universe is left. But which is left? That's completely random. And that's what Einstein didn't like. For example, he said, well, God isn't going to play dice with the universe. That was his famous phrase. It can't be that random. He didn't believe that. There has to be some way of determining it beforehand. That's what he simply couldn't believe. Now, what I'm going to do now is I'm going to just give you a small example, a little puzzle, to try to explain this. So, when I talk about quantum physics to people who don't know anything about it, I feel quite envious of other scientists who work in medicine or who work in chemistry, because those scientists are always able to come up with analogies. We had one yesterday that was great. Well, this is like this, it's like that, it's like, playing basketball, as we heard yesterday, but with quantum physics it's more complicated because there's absolutely nothing like it in the macro world. I mean, what can we think of? What example can we think of in the macro world when someone has lots of properties at the same time? So I'm going to just explain a paradox, and then I'm going to tell you how quantum physics resolves that paradox. So, now these philosophical debates that happened in the 1930s, 1940s, etc., gave rise to paradoxes such as Schrödinger's cat, which basically says, in the microscopic world, particles can be doing many things at the same time. If we extrapolated that to our world, the macroscopic world, then we would have a cat that could be alive and dead at the same time, assuming it was always completely in a very closed box and we couldn't observe it. As soon as we open the box and we observe the cat, that was when the property would be defined and the cat would either be alive or dead. It's not that the cat's there and we don't know whether it's alive or dead. It is alive and is dead at the same time. In one universe it's alive, in one universe it's dead. They both exist until we open the lid, and then only one universe remains and one property is fixed. Now, of course, obviously, this doesn't really work if you do it with cats. If you put a cat in a box, it's going to be either alive or dead in the macroscopic world. And if we really isolated the cat, they wouldn't be able to breathe, and the cat would definitely be dead, so we would know it was dead, because it wouldn't have any oxygen. So, let me give you another situation. This is a photograph of Munich, which is a city where I live. There are a number of different streets here. This street here, you can see, they've all got their own names. We've got the Busker Street, we've got Luis Street, we've got Teresa Street there. And in the experiment that I want to do, there's going to be two people with walkie-talkies. One will be here, and one will be over there. And the person over here is going to let the cars go through. So a car will go through, and there'll be two possible places, two possible paths to get to the end point. They can go up through the top, so they can there choose Louis Street or Teresa Street, or they can go the bottom route, and they can go either up or down. And then one person with the walkie-talkie is going to say, right, a car's just gone by. There's no other cars, just one car. And when it goes past, they'll say, okay, it's gone down Teresa Street. And then the next one they say, another car's gone by. It's going to go this Louis Street, Teresa Street, and then we just repeat the experiment as cars go by. But to make it more similar to what happens in the quantum world, we're just going to turn all the lights out, because we said we can't see, we can't look, we can't observe these properties. So this is represented. There's an entrance point here. Maybe it could be a tunnel, right, where we can't see what happens, but we're still doing the same thing. We've got people with walkie-talkies. Now, just imagine that we carry out this experiment, and cars start going by, and all the cars choose to go down Teresa Street. Well, maybe all of them have decided to do that. They just all decide to go there. Okay, now let's change the experiment a little bit. Now, in Munich there's a lot of roadworks. I'm sure in all cities this is what happens, so there's going to be some roadworks there. So cars can't go past there. All the cars that go past will have to follow the top route, because they can't follow the second route because there's a massive hole in the road and they'd all fall down it, so they can't go there. So we're going to turn the lights out again and see what happens. And we've got the walkie-talkie and they say, right, car's gone by. And the first one comes out Teresa Street. The second one, Louis Street. The third one, Teresa Street. The fourth one, Louis. Okay, this is an experiment that we could have carried out, in which if the street isn't blocked, they all come out Teresa Street, but if that street is blocked, some of them come out of Teresa Street and some of them come out of Louis Street. It's as simple as that. Now, some of you will have realised that this is impossible, right? Why is it impossible? Well, let's focus on the two different routes that we had previously. Let's going to take one of the cars that have gone by. Now, I've turned the lights on, but just so we can see it, but in general, the lights are off. When the car comes along here, in this first situation, if this is open, then it will always come out of this street. We said that in the first experiment, all the cars came out of Teresa Street. And in the second case, one street is shut, but even so, some of the cars go out Teresa Street and some Louis Street. So why? Why is this? Why does that depend on whether another street, completely different street, is open or closed? It's impossible, right? Completely impossible. If you think about it a little bit, there's something going on here. Someone's cheating. Someone's got another walkie-talkie and telling them where to go, and they're saying, look, this street is shut. Or maybe they've gone there and they've turned around and they've gone somewhere else. So this situation in our world, in our macroscopic world, is completely impossible. It couldn't happen unless someone's cheating. But if no one cheats, it's impossible. Well, but in the microscopic world, it could happen. We can't obviously carry out this experiment with cars because you can't isolate a car. We're never going to have this situation. But we can do it with other devices which are fairly cheap and we can buy on the internet. You can buy a laser, like a laser pointer, which I've got here on the internet very easily. We can also buy mirrors, and some of them are beam splitters, so they let some of the light through and not all of it. And we can also buy a detector or a sensor. It's a very small device. It just, costs between 500 and 1,000 euros, and it just goes click, click, click when it detects photons. So you can have the laser, and we could have a mirror there in the middle, letting part of the light go through and deflecting other part of the light. And we would be hearing clicks, because you've got the detectors there as well. So click, 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 click. And this tells us something that we already knew, and that is that light is made up of photons, because the detector goes click every time it detects a photon. So we already knew that, that's fine. Secondly, and this isn't quite as important, but this is all random. There's no way of predicting where the next click is going to come, but that's not so important for what we're talking about here. But now, with the same devices, we're going to recreate the situation I described before with cars. So this is like an analogy. So here we've got a beam splitter. Here's another reflecting different types of mirrors. Now, the photons can either take the top route or they can take the bottom route, and when they get here they can either go to the right or they can go upwards, exactly the same way as the cars, which entered one way, but they could leave the area along two different routes. So it's the same situation, but now we're in the microscopic world. And you can do this in a laboratory. You don't need anything too sophisticated. You can just use the equipment that I've explained earlier. So we're going to turn the lights off. So we're not going to observe where the photons go through. And so we have the photons that go into this area here. They're all detected here. All of them here, click. Which is what we said might happen in the first situation with the cars. But if now what I do is I stop the photons here, and I force all the photons to take the top route, and I also turn the light out, what happens? Well, we detect photons both here and here. So it's the same situation that I explained to you before with the cars, but now with photons. And before I said it's absolutely impossible, wouldn't work, wouldn't ever happen, because the car here would need, there's no way that it depends on whether the car knows that the street below is shut. But in this experiment, those that go take the top route, they need to know what's happening. And that's because they take the bottom route at the same time. And this is what quantum physics describes. And this is what we see in so many different experiments. The photon that leaves here creates a superposition. In one universe, it takes the top route. In another universe, it takes the bottom route. All of this is reflected. And these two universes merge together, and then some of them go out to the right and some of them up the top. In the first experiment, they all go out in the same way. But there's only one universe in the second experiment. So at the top, the superposition is both on the top route, and because there are two universes on the top route, some photons will go out to the right and some photons will go up the top. So in short, this It's not a particularly sophisticated experiment. We can do it at school if you want to, but it tells us that the photons pass through both routes, so there's like a doubling of the life of the photons. We say in a technical terms that it is superimposed, there's a superimposition. We assign the value 0 to the top root and the value 1 to the bottom root, so it's either 0 or 1 all the time. And it also tells us that once we have these two universes, when we observe, when we carry out a detection, when we put the detector there, then one of the universes disappears and only one remains. Now, I know that most of you are going to think this is very strange. And last time I was here, I told you about my grandma. She came from Galicia. She hadn't, gone to school for very long. She was the eldest of many, many siblings, and she had to leave school to look after her siblings very early. And when I was doing my PhD thesis, I was trying to explain this to her. And she said, yeah, Ignacio, that's all well and good, but just don't tell anyone else about it, because they're going to think you're a little strange. Now, today we have much more sophisticated experiments, and we can prove with these experiments that no one's tricking us, that this is actually real. And this is why these gentlemen won the Nobel Prize in Physics last year, in fact, because they saw that, nature is weird, it's strange, these things do exist, but you can actually prove this experimentally.
So once we've understood these extraordinary features of quantum physics, we can create and uncreate universes as we like. So now we'll have many philosophical questions, of course, because maybe things that happen around us are not defined, and it's only when we observe them that they are actually fixed and defined. So nothing is written. What's happening is being written as we observe reality. And at the same time, this is telling us that on that side of the mirror, we can do extraordinary things. And I told you about the cars. This cannot happen in our world, in the macro world, in the non-quantum world, but it can happen in the quantum universe. So we can do things there, we can carry out things there that would never happen in the macro world. So we need to use these extraordinary laws to process, transmit, and obtain information in a different way, so that we have possibilities that we don't have in the existing communication systems and computers. The truth is that when we speak about quantum computers, they don't work so much with photons. They work with other properties of physics. They don't work with the road of photons, but they focus on the properties of magnets, for instance. As you may know, a magnet has a north side and a south pole to it. North pole could look up and North pole could look down. And according to quantum physics, if there are two possible positions, we can also have the superposition of both. We can have an electronic circuit where the electricity is flowing clockwise or counterclockwise. According to quantum physics, we could have both at the same time. Here we have macro materials. We are not going to observe any quantum property there, but if we go to the micro world, what will we see? We have small magnets, small circuits, where we can do everything I just told you about. In fact, an atom is a little magnet. It has what we call a bipolar moment. It behaves as a magnet, and therefore it can have a north pole looking up, and it could be one north pole could look down, and that could be the zero position. And according to quantum physics, we could have both superimposed. And if we look at superconductors at the micro level, we can observe the same properties, not just with photons, but also with atoms or superconductors. And the situation becomes even more interesting if we take many of them. If we take many atoms, many superconductors together, one after the other, we can put all the atoms with the northern pole looking up in the 0, 0, 0, 0 position. Or we can have them all looking upwards and maybe one of them looking downwards. And that would be the position 0, 0, 0, 0, 0, 1. And we can have some looking up and some of them looking down. And there is an exponential number of configurations of magnets. 0, 0, 0, 1, 0, 0, 0, etc., etc. It's 2 to the power of n, where n is the number of atoms that we have. So according to quantum physics, all those configurations can be happening parallelly. in different universes, in parallel universes. Which means that we can have 2 to the power of n, an exponential number of universes that are occurring at the same time, but only with n atoms. And this is what gives power to quantum computers. If you know about exponential laws, you probably know that they are spectacular. It's like if we had like 300 atoms, the number of combinations, the number of possible superpositions would be 2 to the power of 300. And that is like 10 to the power of 80. It's like 1 followed by 80 zeros. That's greater than the number of all particles, baryons that we have in the universe. So only with just 300 atoms, we could have superpositions of so many possibilities that we could not even imagine. So a quantum computer, what it does is precisely that. It uses these superpositions, these laws of quantum physics, to make parallel calculations in one universe, and they carry out one calculation, in the other one another one, and since we've got so many of them, we can carry out so many calculations at the same time, and this makes them very powerful, much more powerful than the currently existing computers. This is what Feynman called the quantum parallelism of computers, of quantum computers. However, this is not all. Even if I have these superpositions of so many possibilities of carrying out parallel calculations, in the end, I will have to observe, look at them. I want a result for my calculation, but then as soon as I observe it, every calculations will disappear, all but one. So what's the benefit, the advantage of having all these calculations? Well, we're not based or focused on these parallel calculations. What we do is that we're using, as we were using the mirrors earlier on, we're going to use calculations to use superpositions in a very special way so that we can carry out calculations in a different way. So in fact, quantum computers, what they do is that they make the most of all these possible superpositions and make the most of interferences, because when we have superpositions, we just get one result. So a quantum computer will create these superpositions, it will carry out parallel calculations, and then it has to think how it can use and combine these superpositions so that in the end we get one result, and it's the right one. So quantum computers make the most of these superpositions to be more efficient, safer, and precise, accurate. So if we take a step back, we could say that quantum computers and quantum computing is not about doing things faster, carrying out things faster. They carry out calculations in a different way. In the past, we used abacuses, we used mechanic laws, and then we used electronic laws. We had electronic computers, and now we have new laws, the laws of quantum physics, which enable us to do things in a different way. And this is the advantage of quantum computers. A takeaway message for you: a quantum computer is not faster, really. It's just different. It's a different way of doing things, of making calculations. And what are the calculations we can carry out with quantum computers? Well, we know that we can use them to solve specific problems. For instance, problems related to cryptography. We can also use them to solve scientific problems that we cannot solve with supercomputers related to physics, chemistry, material physics. And we have evidence that they will help us in industrial processes to optimize things in the field of artificial intelligence. But we're very, very sure that quantum computers are very accurate when it comes to solving problems concerning chemistry, physics, and cryptography. So we could wonder, well, if all these superpositions will just help us to solve scientific problems, well, how is this going to help us in my daily work? Well, they might be very helpful for people working at the IPC, but Well, to answer this question, I would like to go 80 years back when the first classical non-quantum computers were being developed. You see, we have the Colossus here. And these computers, when they were created back then, they had two applications. They can be used to solve scientific problems and to decode messages. And little by little, people would use them more and more, and so new applications were found. So I think that we may have the same attitude concerning quantum behaviors. There are so many possible applications, but we still need to find out about them. So this is another takeaway message for you. We know some of the applications of quantum computers and quantum computing, but probably as we develop all this, we will be finding more and more possible potential applications. So every time we cross a technological border and have access to new laws, we find new applications that we couldn't imagine beforehand. So we've got a number of different technologies that are being developed by a number of different platforms that are building quantum computers. We've got many horses in this race of quantum computers, based in trapped ions, for instance. They have like 40 atoms, which we call qubits, 40 to 50. We have superconductors. I've already told you how they work. They have like 127 qubits, and IBM computers will have 400 qubits. We also have other atomic systems called Reaper atoms, which are making headway lately. They have 300 to 400 qubits. And we're also researching into how to build quantum computers in photonics and other fields and platforms. So what I mean is that this is work in progress. We, of course, have some prototypes, like the three that you see at the top of the slides that carry out calculations that are more powerful than the current computers. This is still work in progress. And the reason why we don't have them here is that quantum physics is highly sensitive. We've said that as soon as we observe or interact with what's going on, superpositions disappear, and we can no longer make the most of that advantage that quantum laws give us. It's very hard to isolate all these systems, and therefore mistakes are made. Yes, prototypes of quantum computers, you know, sometimes one of these qubits change. They have these zeros and ones, and suddenly one of them changes. So the mistakes could happen, and there are two ways that are being used to correct these mistakes. Well, one of the things we can do is to try and correct the mistakes, but that would take some time. That would lead to quantum computers with error correction possibilities. And the second is to learn how to coexist with these mistakes and errors, because, well, we can move forward and not correct the mistakes, the errors that are occurring, because even if we don't have a precise result, that information we're getting can be very, very interesting. So this is a timeline concerning quantum computing for you to know where we come from and where we're heading for. The first prototypes were built in an academic context in 1996. In 2012, Google, IBM started working in this field, and then in 2019, the quantum supremacy was announced with that type of quantum computer, even with errors being made. Calculations can be carried out, calculations that we cannot carry out with supercomputers. And now we've come to the NISQ era, where we have quantum computers with mistakes, noisy computers that will help us to solve problems, even though mistakes are made. And then later on, we don't know when, in 5, 10, 15 years' time, we hope we'll be having scalable computers, quantum computers. So this is the NISQ era. We have prototypes that make mistakes, and now the main question we may ask ourselves is precisely we need to use these computers. This is something that will be carried out here in Donostia, in San Sebastian. We need to use these computers and then see what happens. And I'm coming to the end of my presentation. I would like to finish by saying that quantum technologies are undergoing an extraordinary moment in time. We've been waiting for this moment for a long time. We wanted to be able to talk about this and show something that was actually working. There are already a few applications up and running, and we're researching into some other ones in the short term. I've mentioned a few of them. And probably what we're going through currently, even if we are not fully aware of it, is a quantum revolution, a second quantum revolution, where these applications will be useful in our daily lives. And my final message would be that probably the main application of quantum technology is yet to come. Thank you very much for your attention.